Hey everyone, and welcome. Today, we are going to get right into a super important part of your real numbers chapter, the division algorithm. We're going to see how this one simple idea builds up into a powerful tool called Euclid's algorithm, which will let you solve some really tricky problems. So, let's get right to it. God made the integers. All else is the work of man. Pretty deep, right? But this quote from Leopold Kronecker is actually the perfect way to kick things off. It reminds us that at the heart of it all, integers are the basic building blocks of mathematics. Today, we're going to explore how they work to build some serious problem-solving skills. Before we dive into the formal stuff, let's warm up our brains with a quick puzzle. So, picture a swarm of bees in a garden. They follow a very specific set of rules when they land on flowers, and our job is to play detective and figure out exactly how many bees are in that swarm. Okay, so here are the clues. If the bees try to land on 2 flowers, there's always 1 bee left over. If they try 3 flowers, 2 bees are left. On 4 flowers, 3 are left. But, and here's the big clue, if they land on 5 flowers, every single bee has a flower, with none left over. Oh, and we also know there are 50 bees or fewer. Each of these little rules is really just a statement about division and remainders. So how in the world do we solve this? Well, that last condition is our key. When the number of bees is divided by 5, the remainder is 0. That means the answer has to be a multiple of 5. So let's just list out the multiples of 5 that are less than 50. 5, 10, 15, 20, 25, 30, 35, 40, and 45. Now we just have to test these numbers against the other rules. And when you do that, you'll find that only one number fits all the conditions. 35. Let's double check, right? 35 divided by 2 is 17 with a remainder of 1. Perfect. 35 divided by 3 is 11 with a remainder of 2. Perfect. And 35 divided by 4 is 8 with a remainder of 3. It works. You see, that bee puzzle was way more than just a bit of fun. That whole process we just went through, thinking about dividing numbers and what's left over, that is the exact logic behind a huge fundamental principle in math. Let's see how it connects to our first big topic. And here we are, the division algorithm. This is basically the official mathematical rule for what we just did with those bees. It might sound fancy, but it's really the foundation for so much in number theory. Now, don't let the formal definition intimidate you. It all comes down to this one simple-looking equation. A equals B times Q plus R. All it's saying is that if you take any 2 positive integers, A and B, you can always find a unique quotient Q and a remainder R. The most important part, the rule you absolutely have to remember, is that the remainder, R, has to be greater than or equal to 0, but always less than the divisor, B. Let's just do a quick breakdown of those variables so we're all on the same page. A is the dividend, that's the number you're starting with. B is the divisor. Q is the quotient, which is the main result of the division. And of course, R is our good friend, the remainder. What's left over?
Let's see this thing in action. It makes it so much clearer. Look at that first row. If our A is 13 and our B is 3, well, 13 equals 3 times 4 plus 1. So our quotient Q is 4 and our remainder R is 1. Simple, right? Now look at 80 divided by 8. The remainder is 0. As you can see, this formula gives us a really nice, consistent way to look at any division problem.
Okay, so now we get what the division algorithm is, but what can we do with it? Well, it turns out it's the engine behind a super clever and efficient method for finding the highest common factor, or HCF, the biggest number that divides 2 other numbers perfectly. This amazing method is called Euclid's algorithm. So, let me ask you this. How would you find the HCF of 2 really messy numbers, like 1651 and 2032? I mean, you could try to list out all their factors, but that would take forever, and you'd probably make a mistake. This is exactly where Euclid's method is a total game changer. Let's walk through this with a simpler example first. Say 160. First up, we just apply our division algorithm. We divide 100 by 60. That gives us a quotient of 1 and a remainder of 40. Now here comes the magic trick of the algorithm. The old divisor, 60, becomes our new number to divide. And the old remainder, 40, becomes our new divisor. So we divide 60 by 40 and get a remainder of 20. We just do it again. Now we divide 40 by 20. And what do we get? A remainder of 0. And as soon as you hit 0, you stop. The process is over. So, where's the answer? You're going to love how simple this is. The HCF is simply the divisor from the very last step, the step right before you got that 0 remainder. In our case, that was 20. And that's it. The HCF of 160 is 20. It's such a clean process, and it always works. All right, now that you get the method, let's put it to the test with some questions you'd actually see on a board exam.
First up, let's find the HCF of 900 and 270. Step 1, we divide 900 by 270. That leaves us with a remainder of 90. For step 2, our old divisor, 270, moves over, and our old remainder, 90, becomes the new divisor. We divide 270 by 90, and what do you know? We get a remainder of 0. And just like that, in 2 steps, we're done.
Since the process stopped when we hit a remainder of 0, we just look back at the divisor from that last step, and that was 90. So the HCF of 900 and 270 is 90. See how fast that was? Okay, now let's tackle that tougher problem from earlier, the HCF of 1651 and 2032. Let's just follow the steps. Step 1, 2032 divided by 1651 gives a remainder of 381. Step 2, 1651 divided by 381 gives us a remainder of 127. Step 3, 381 divided by 127 gives us a perfect remainder of 0. And that's our cue to stop. The divisor in that final step was 127. That means the HCF of 1651 and 2032 is 127. A problem that looked like an absolute nightmare was solved cleanly in just 3 steps. That's the real power of Euclid's algorithm. Okay, time to level up. Finding the HCF is one thing, but the division algorithm is also your secret weapon for those more abstract proof-based questions, the ones where you have to prove that something is always true for certain types of numbers. Let's tackle one together. Here's a classic exam question. Show that any positive odd integer must be of the form 4q plus 1 or 4q plus 3. Now I know it looks a bit scary and abstract, right? But trust me, the solution is just pure, simple logic. And it all starts with the division algorithm.
Let's break this down step by step. We start by just picking any positive integer. Let's call it a. Now, since the question talks about the form 4q, that's our hint. We're going to use the division algorithm with a divisor of b equals 4. So according to our rule, a has to look like one of 4 possible forms: 4q plus 0, 4q plus 1, 4q plus 2, or 4q plus 3. Those are the only options. But the question specifies that a has to be odd. So let's check our options. Is 4q ever odd? No, it's 2 times 2q, so it's always even. What about 4q plus 2? We can factor out a 2, so it's 2 times 2q plus 1, which is also always even. So if our number a has to be odd, it can't be 4q or 4q plus 2, which means the only possibilities left are 4q plus 1 and 4q plus 3. And that's it. We've proved it. This exact same logic is how you solve all of these proof questions. Whether it's proving something about the square of an integer or the cube, you always start with the division algorithm, list out the possible cases based on the remainders, and then eliminate the ones that don't fit the conditions of the problem.
We've gone through the theory, and we've put it into practice. Now, let's wrap this up with a clear game plan. How to present your work on an exam to make sure you get every single mark you deserve. Okay, this is your exam day checklist. First, and this is non-negotiable, you must show every single step of Euclid's algorithm. Don't do it in your head. The examiner needs to see your process. Second, make it really easy for them to follow along. Highlighting or just underlining the remainder in each line is a great way to do that. Third, always finish with a clear concluding sentence, like, therefore the HCF of this number and that number is. And finally, put a nice, neat box around your final answer. These little things show you're confident and make it easy for the examiner to give you full credit. So think about where we started. A simple little puzzle about bees in a garden. And that one idea led us to this incredibly elegant and powerful algorithm that can solve really complex problems and even prove fundamental truths about numbers. It just goes to show you that math is full of these beautiful hidden patterns. The real question is, what will you discover next?